So we kind of got two big problems to work through to kind of show how you can use these different equations and how they actually play out in the field of astronomy. Then we'll talk about like how the perception of gravity has changed, like how it started and what we think it was, and then how role of Newton, and then how Einstein ended up changing it, and then we'll actually morph everything together into kind of one big set of equations. So when you look at how this is what we talked about, like, okay, we want to figure out what's the mass of Saturn, Jupiter, the Earth, whatever it is. We can't stop these planets, put them on a scale and go, oh, hey, this is what we have. So what we do is we observe things that are in orbit around them. And once we make those observations, then we work backwards and we figure out what the mass of the planet is, because we can't directly measure that value. So here's kind of a typical problem. So we're looking through the different, one of the famous ones that we look for called extra planets, which are outside of our solar system. Actually, there's one named Kepler, okay, because they use that to look for different planets. And so we make an observation, and we show that we find it has a moon that has an orbital period of 20.5 hours. And here's the radius, and we want to figure out the mass of the planet, okay? So there's a couple of things to look for when I give you radius, okay? Remember that radius always has to be a center-to-center distance, because we treat everything as being a point mass. So if on this problem, when I say, hey, it has a radius of 3.68 times 10 to the 6 meters, that is already from the center of that planet out to that moon. Okay, you don't have to add in anything to it. Now, in contrast to that, if you look at that problem that we worked yesterday I said, hey, this thing is 122 kilometers above the surface. So if I tell you that it's above the surface, then you have to add in the radius of the moon, the planet, whatever that is, okay? But if I just tell you straight up, that's the radius, you don't have to do anything with it, okay? That's the number. That's all you have to do with it. That's it. Just accept it. So here's what you've got on this one. You've got, if you look at the information that you've got, it's going to take 20.5 hours to go around, which is relatively fast, okay, for a moon, because if you consider like our moon takes 28 days to go around, okay, if you haven't noticed, we're about to approach the full moon, okay, so if you, like tonight, when you look, it's supposed to be clear tonight, look off to the east about sunset, you'll see the full moon rising, okay, or if you're up tomorrow morning, you'll see that full moon setting just before sunrise. So here's the setup. So we've got the orbital period, we have the radius, we're trying to find the mass of the planet. So the only thing you can use is that 4 pi squared r cubed equals big G mass times t squared, okay? So this is the most generic one, because you can use this to find three things: orbital period, radius, or mass. So you need to solve this thing for mass. So, okay, 4 pi squared r cubed over gt squared. Now, here's what you have to be very careful of. That 20.5 hours is going to be your downfall, because you're going to see that and you're going to go, oh, there's my period, I'm going to put that as 20.5 hours, okay? And you're going to leave it in hours, and you're going to get an answer that makes absolutely no sense. I beg of you, okay, I beg of you, anytime you see big G in any of these calculations, it has to be this MKS system as meters, kilograms, and seconds, okay? It has to be that way, because lurking within that G are newtons, which are kilograms, meters per second squared, okay? So if you look at what happens, this period has to be in seconds squared, because that's the only way you can get time to cancel out, okay? So you mark my words. You all right now go, oh, Mr. Burkamp, we won't do that. Don't be silly. We won't leave that in hours. Yes, you will, okay? Trust me. I'd like to think that you wouldn't, but realistically. But but I'm gonna make this appeal. My hope springs eternal, that at some point before I retire, one class, and maybe it's you guys, on this test, you won't make that mistake, and you're gonna take those hours and you go, oh, I'm gonna work those in seconds. Okay, so we got 4 pi squared. The radius is already in meters, so that's not a big deal. So we got 3.68, whatever that is, times 10 to the 6th meters. And that's got to get cubed. And then we've got big G, 6.67 times 10 to the negative 11th kilograms squared. Now, you got to take that 20.5 hours, and in 1 hour, that's 3,600 seconds. Now, here's the other thing that's going to happen. You mark my words. You're going to be so happy that you remembered to convert the hours into seconds. Okay, you're just like, did that. That's me. But then you're going to forget to square it. Okay, that happens too. It's like you get so excited, like, oh, I remember to convert it into seconds, and then you're going to forget to square it, and then you're going to get an answer that doesn't make any sense either. So, run the numbers, let me know what you get.
Something wrong?
Yeah,
Okay.
it's not that big. That would be like, that would be a black hole.
Okay.
Because Carson, even if you look at this order of magnitude, up on top, you have 10 to the 18th, and then you're dividing by 10 to the negative 11th, so that puts you 10 to the 29th, and then you're dividing by time squared, so it has to be less than 10 to the 29th.
Yeah.
Can it be 10 and the 21st?
Oh yeah, that's cool. What'd you get?
3.4478 times 10 to the 21st.
Wait,
Whoa.
I got 5.416 times 10 to the 24th.
yeah, that's what I got.
Okay.
We need yours.
I could be wrong.
Well,
Did you get something different? We built to be wrong.
I got the same thing.
you got the same thing?
Us 3.
Okay. So what'd you get?
5.416 e to the 21st.
Kilograms. Okay, everybody cool with that? Carson, are we okay?
Yeah.
Okay, make sure that you can get this answer on your calculator, okay? Make sure that you see how you got that. Okay, so at that one done, boom, you're gonna have a problem like this. I promise you, on Thursday, if you hand in that test and you haven't done a problem like this where you use that information to find the mass of one of the planets in our solar system, you have done something horribly wrong, okay? I promise you, it's going to be there, okay? Second to the last page, there it's going to be. Okay. Now, so this is a similar type idea, but it's a different version of it. So on this one, now let's say, for example, we had information about the moon. So there's a couple of things about moons that orbit planets. Number one, if you know the information about the moon, you can use that to find the mass of the planet. Oh, okay, so cool. So imagine this, you're on Star Trek, you're exploring a new planet, you're the science officer. And you approach a planet and you observe that it has a moon. Okay, well let's figure out the information from the moon, let's find the mass of the planet. Okay, cool, got that. Then it's like, okay, now we're going to land on the moon. Okay, well now we're actually going to land on the moon. Okay, we're going to land on the moon.
Oh,
So we're standing here on the moon. Okay, we have touchdown. And we know the radius of the moon, okay? And we land on the moon and we set up a pendulum. That's the easiest way to do it. And we figure out that the gravitational acceleration on that moon is 1.22 meters per second squared, which is obviously much less than it is on Earth. Oh, that's 9.8 meters per second squared. Oh, okay, cool. They're going to be 1.22. Great place to go vacation if you want to like play basketball and dunk. Okay, it's like, oh, geez, only 1.22 meters per second squared, right? I'm old. I can dunk on this planet, okay, because of the fact that it has such a low gravitational field. Golf would be cool. It's like, man, you crunch the ball, okay, and it probably doesn't have an atmosphere because it has such a low gravitational field. So now we want to figure out the mass of the moon, and this is what we did on the Apollo 11 missions, which was the first missions that actually landed on the moon. This is what they did. They took along a pendulum, and they measured the gravitational acceleration on the moon, so they knew what little g was. Then we knew the radius of the moon, had that number. So what was cool is that we landed on the moon. We didn't know the mass of the moon. We had a pretty good idea of what it was. We didn't know the exact mass of the moon when we landed on it. Okay, so then you go to little g equals big G, mass of the moon over r squared. Okay, so this little g is when you drop an object, what's it going to be, that acceleration? So to give you some perspective, if you took this equation and plugged in the mass of the Earth and the radius of the Earth, you would generate a value of 9.8 meters per second squared, okay, on an average radius. Now, obviously, if you go to the top of Mount Everest, where that R is a little bit bigger, G is going to be a little bit less, okay? So little g is not a constant, okay? That changes if I'm on the Earth, if I'm on the moon, even even on the surface of the Earth. Little g is not a constant. We use 9.8 meters per second squared because that's on average, that's what it is. But in reality, that number changes. But here's what I want you to understand about this. That acceleration, there's a couple of things I want you to remember about this. Number one, it's on Earth, it's not constant. It changes depending upon where you are. The other thing that's important is that the mass of what you drop doesn't affect the value of little g. So if I drop this big massive steel marble, okay, or if I drop this piece of plastic, that calculation of little g only depends upon two things. The mass of the Earth, or the mass of the moon, or whatever you're falling towards, and how far you are from that center. The mass of what you drop doesn't matter. Now, does the steel ball weigh more? God, yes. Okay, absolutely. But it also has more mass. It has more inertia. So it takes more force to end up with that same acceleration. Okay? All right. So we know everything except for the mass of this moon. So we're going to have g squared divided by big G, and boom, there's going to be our mass. So we're going to have 1.22 meters per second squared times our radius of 1.40 times 10 to the 5th meters, and that's going to get squared. And then I'm going to divide that by 6.67 times 10 to the negative 11th. Now, look at this just in order of magnitude. Oh, I have 10 to the 5th. That's going to get squared. That's going to get me 10 to the 10th. Then I've got 10 to the 10th divided by 10 to the negative 11th. That's going to get me 10 to the 21st. So as a ballpark, okay, just a ballpark answer, I should get something around 10 to the 21st. Okay, that just tells me this order of magnitude. So if I punch this in, and if I get 10 to the 40th, I've done something horribly wrong. Okay, if I get 10 to the 10th, I've done something horribly wrong. So this order of magnitude at least gets you an idea of what your answer should be. Okay? So what'd you get?
I got 3.585 times 10 to the 20th.
Times 10 to the what?
20th.
20th. Cool? Everybody good with that number?
Yep.
Okay. All right. So there we go. Now here's the last thing. What would be the distance from the center of the moon so that a 1 kilogram mass weighs 1 newton? Now here's what I want you to think through. If you're on the surface of this moon and you have a 1 kilogram mass, okay, you have a 1 kilogram mass, and you're on the surface of the moon and you have a Newton scale, okay, you have a 1 kilogram mass, you have a Newton scale, you're standing on the surface of this moon. What would a 1 kilogram mass weigh? Do not make this difficult.
1.22.
1.22 newtons, right? You take mass times your gravitational acceleration. You take 1 kilogram times 1.22 meters per second squared, and it would weigh 1.22 newtons. You take that same mass and you put it on Earth. That's going to weigh 9.8 newtons, okay? You take it to Mars, it would weigh 3.7 newtons, okay? So if you're standing on the surface of this planet, a 1 kilogram mass would weigh 1.22 newtons. And again, here's the terminology. Mass versus weight, okay? Mass is reflective of the interaction with the gravitational field. Mass is just a number. It's a measure of how much stuff there is, okay? So, here's the story. If I want this to weigh 1 newton, okay? So think about this. If I'm on the surface of this moon, it weighs 1.22 newtons. So Peyton, if I wanted to weigh 1.22 newtons, do I need to go further away from the surface of the moon, or do I need to go inside the surface of the moon?
Can you repeat that?
Okay. I want if I'm standing at the surface of the moon, it's going to weigh 1.22 newtons. Okay? Because G is 1.22 meters per second squared. Cool with this?
Mm-hmm.
So I want to go somewhere where that 1 kilogram mass only weighs 1 newton. Okay? So do I go further from the center of the moon, or do I go like closer to the center? Do I go further from the center or closer to the center? Yeah. So I've got to go at some distance away from the surface of the moon. So that way the gravitational field becomes weaker. Okay? So I'm going to go to this. The little g equals big G mass over r squared. So at this point, I know the mass of the moon. I have that number. Okay? I know what big G is. I know little g is going to be 1 meter per second squared, because that's what G would have to be for 1 kilogram to mass to weigh 1 newton. Okay? So then I got that. The only thing I don't know is this R. So I'd have GR squared equals big G times the mass, divide by little g, and then take the square root of all of that. So that's going to be R equals big G, mass of the moon, over little g. Now, that mass is not the 1 kilogram mass, okay? It's not it. It's the mass that it's following towards, right? So don't plug in 1 kilogram there. You have to plug in the mass of the moon itself, or the earth, or whatever this is. So you've got, and then you've got the, what do we get from 3 point, what was that, 585 times 10 to the 20th kilograms divided by 1 meter per second squared. So now, obviously, what does your answer have to be bigger than? Well, yeah, it's got to be bigger than the radius of the moon. So if you do this and you don't get an answer bigger than 1.40 times 10 to the 5th meters, you've done something wrong. So that answer has to be bigger than the radius of the moon. So, what'd you get? And don't forget to take the square root of it.
I got 1.546 times 10 to the 5th.
I got that too.
Okay? There you go. Now, if I asked you, here's the other variation I could have on a problem like this. I could say, how far above the surface of the moon do you have to be to make this happen? So if I said, how far above the surface, you would take that distance and then you would subtract out the radius of the moon itself. So if I said, how far above, you'd subtract 1.40 times 10 to the 5th meters, and then that would get you that distance that's above the surface of the moon. So here's the story. When you see surface of the moon, surface of the earth, something like that, okay? All that's saying is you're either going to add or subtract out the radius of that planet, okay? Just depends upon the situation. Okay, so we got this. There's only a certain number of equations on this test, okay? I don't have that many tricks up my sleeve. So now we kind of get an idea of how to use them. So let's talk about how this plays out. So if you look at the history of gravity, and it sounds odd, but for a while, gravity was perceived as being magic. You're going, how could gravity be magic? Well, let me put it this way. So let's say that I take this model of a water molecule, one oxygen, two hydrogens, and I put it there, and I put my hand over the top of it, and all of a sudden, that little plastic water molecule begins to levitate, and it begins to accelerate up towards my hand. Okay? And you all would flip out. It's like, where comes the Jedi? Okay, it's magic. Okay, and I would say, why is it magic? And you would say, well, it's moving, but there's no observed direct force that's causing that movement. So if I do this and it goes, whoop, you'd go, oh, it's magic. Okay? Because there's nothing that you observe that's visible that would make this thing move towards my hand. Now, if I hold it in my hand and I let go of it, oh, that's just gravity. Okay? Well, you can't see gravity. It isn't like there's little strings or something like that. It isn't light where it's visible. Okay? You can't feel it. So, if this thing moves up towards my hand, that's magic. If it falls away from my hand, that's gravity. But in both situations, there's nothing observable. There's no physical connection between this water molecule and the earth. Oh, it just happens. So that's why if you look at a definition of what magic is, oh, something moves without it physically being contacted. Gravity does it all the time. So that's why I said if you accept a certain definition of magic, gravity is viewed as magic. Okay, that's kind of weird. Well, yeah, okay. So fast forward to Kepler. Read Kepler's works. Kepler was like a reporter. Okay? He goes, look, here's the story. They move in ellipses, they move faster when they're closer, they move slower when they're further away, they sweep out equal areas in equal times, okay? And then his third law is TA squared over TB squared equals RA cubed over RB cubed. Cool. Okay? He really didn't try to explain why it worked. He's just like the reporter. He goes, here's the story. Don't know why it works, but it works. So he did his work in the early 1600s, okay? Late 1600s, Isaac Newton comes along. And Isaac Newton says, hey, let's talk about gravity. Got this really cool equation that F equals big G M1 M2 over R squared, okay? And Isaac Newton was a big idea kind of guy, okay? Isaac Newton never actually found the numeric value of G. Okay, didn't do it. He says, I got other things to worry about. I'm trying to invent calculus. I'll leave that to someone else. Okay? So Henry Cavendish was the one that actually found the numeric value of G. Took the large masses, knew how far apart they were, knew how much force it took to make them move. He found big value G. Then once he found the big value G, then he was able to use that into this equation. So we knew what little g is on the Earth. Set up a pendulum, you got little g. We've known the radius of the Earth since antiquity. He now had the value of big G. He solved for the mass of the Earth. Cool. Okay, now that was his claim to fame. He was the first person to weigh the Earth. Okay, so according to the legend, and it's true or not, but it's a good story. So a colleague of Isaac Newton was sitting there going, mind you, this is late 1600s, so Kepler's work had been published. And he's talking with Newton, and he goes, nobody really understands why Kepler's laws work. And Isaac Newton, supposedly, according to the story, opens up this desk drawer, goes like this, pulls out, excuse me, speaking of going into orbit, okay, pulls out this piece of paper and says, here's the proof, this is why it works. And the guy says, why didn't you have this published? Why haven't you made this known? And Isaac Newton goes, well, it's not that big a deal. It's pretty simple. So it's according to the legend. So let's say that we want to compare, here's the sun, and here's the Earth, and here's Mars. Okay? So let's pick on the same planets that Kepler did. So Newton says, okay, let's look at this as a ratio of their orbital periods. So again, it goes back to the idea that if you look at, let's say, if you look at the Earth, okay? Well, obviously there's a centripetal force acting on the Earth, or otherwise we wouldn't orbit around the sun. So that would be, if you look at that centripetal force, you could write that out as going, okay, that's 4 pi squared r cubed, and that would be the radius of the Earth. And then that's going to equal big G, then t squared, and that would be of the Earth. Okay? So if you wanted to, you could solve this for the period of the Earth, radius of the Earth, whatever. And then also there's the mass of the sun. Okay? Because that's going to, excuse me. Where does mass go on that one? I completely blanked out. No, the mass, that's the mass of the Earth. Okay? Now, then if you want to compare that to Mars, then that would be 4 pi squared. And then you'd have the radius of Mars cubed, and then you'd have big G T period of Mars squared. Okay? So then that would be the mass of the sun, because that's what's at the center. So here's the point. If you look at this as a ratio, okay, well, the 4 pi squareds cancels out, the big G cancels out, and the mass of the sun cancels out, because that's what's at the center of that orbit, okay? So what you're left with then is Kepler's third law that says, oh, the radius of the Earth cubed over the radius of Mars cubed is going to equal the period of the Earth squared over a period of Mars squared. So Newton just goes, here, this is why it works, okay? It's not that big a deal, because all you have to do is set it up as a ratio. But the cool thing about this is why you can only compare things that orbit the same center, because you have to be able to cancel out the mass of what's at the center. So if you were to try and do this with our moon and a moon of Saturn, you couldn't do that, because they have different orbital masses that are orbiting around. So this is why Kepler's third law works. And Isaac Newton pretty much says, there you go, this is why it works. Oh, okay, that's kind of cool. So Newton tied it all back together. So that was in the late 1600s. So now we had the mathematical equations. And it was cool. This actually turns into a philosophical debate. So like if you know, like for example, when I was driving to school, the moon was setting. Okay, it was full moon, pretty cool, it was setting over here. And so this is where you have a philosophical tie-in. It's like, okay, if I know the position of the moon, certain point in the sky, and I know its distance, and I know all the forces acting on the moon, I can tell you exactly where that moon is going to be a year from now. I can tell you when the next lunar eclipse is going to be, when the next solar eclipse is going to be. I can work backwards in time and go, okay, well, there was a solar eclipse at a certain point, okay? Even if you look at, supposedly, it's a good story. So Columbus actually knew he was at the, he was trying to get food from the natives and take it back to Spain. And they were like, we're not going to give you the food. And he knew there was going to be a solar eclipse like the next day. And this is this is in the 1600s. And he basically said, hey, if you don't give me the food, then I'm going to blot out the sun tomorrow. And so, sure enough, they didn't give the food, and then supposedly the solar eclipse happened, and the natives flipped out and said, oh, you can control the sun, and you're powerful, and oh, here's the food. Okay? Whether it's true or not, it's a good story. But here's the point, is that you can predict where events that are going to happen. Coming up in April, there's going to be a solar eclipse. It's not going to be completely visible here. It's going to be more in the southwest part or southeast part of the United States. But we can look forward, we can tell what's going to happen. So then if you apply that idea, you can work backwards, okay? I could tell you where the moon was on your birthday. Okay, you were born on a certain date. I could work backwards and say, well, this is where the moon was. So if you have all the information about the planets, the moon, the earth, whatever, then you can predict where things are going to be in the future, and you can tell where things were in the past. And the planets don't get to vote. Okay, this is all the forces that are acting on them. So this is where it becomes philosophical. Then it's like, then does that apply to us as well? If I know all of the forces that are acting on a system, then does the system actually get to vote? Or is the system just a reflection of the forces that are acting on it? So let's say, for example, you like to play bingo, okay? And the bingo balls are all bouncing around inside a cage. And if you know the position of all of the little bingos, okay, balls, have it written on them, and if you know the motion and all the forces that are acting on them, you can tell in a certain point of time that at exactly 9 o'clock, B4 is going to be pulled out. If you know all the forces that are acting on it, you know at B4 at 9 o'clock, that's the one that's going to get pulled out. Okay? So then the question is okay, do we live in a deterministic universe? Is me sitting here at 8:15 on April 4th in room G20, did I have a choice in this and explain to you all the motions of the planets? Or is this just something that was predestined based upon the initial conditions of the universe? So the universe formed, boom, we put in motion all the events that happened, and Burkamp didn't wake up this morning and go, what am I going to do? I'm going to give him the test now. What am I going to lecture on today? Little Bo Peep, motions of the planets, Shakespeare, I don't know. What am I going to talk about? Let's talk about gravity. It's kind of what we talk about in here. So the argument is that we don't have free will. Okay? The moon doesn't get a vote where it's going to go. It's going to happen. But here's the problem. That's where it gets philosophical. You go, wow, right. I was just destined to do these things. You go, well, I went and I killed someone. Why? Oh, that was destiny. Okay? That was what was formed by the universe, and I was just acting that out. It's like, this is where the argument fails. And this is where quantum mechanics comes into it. It's called Heisenberg uncertainty principle. You cannot know the position and momentum or the velocity of an object at the same amount of time. There's always a large amount of uncertainty in the subatomic particles. Yes, it works well for large objects, but it doesn't work well for small objects, and that's what the universe is made of. And so that's why there's this determinate idea. So it works well with the moon. I can tell you where the moon's going to be, but to be able to say, hey, in 10 years, I know Izzy is going to be in New York City being a famous author or researcher or something like that, based upon a certain set of conditions that exist in the universe. Okay? It doesn't work that way. Now, so now we're going to fast forward. Late 1600s, early 1900s. Albert Einstein has come along. So Einstein's kind of a unique character. There's a whole lecture on his theory of relativity. But Einstein viewed space and time as a continuum. So let's go to the back and I'll kind of show you how Einstein viewed space and time. So stop that and then bring that with me. What Einstein viewed space and time is like spandex, okay? So he viewed space and time as this flat area. So you can actually do a lot with this. So here I've got like this very small object, and I roll it across, and you'll notice that it pretty much rolls in a straight line, okay? So that's basically, you can look at all of Newton's laws in terms of this. Oh, okay, I get it rolling, okay? Well, an object in motion maintains motion until an outside force acts upon it. And you'll notice that it also travels in a straight line because there's no forces acting on it. So if this is like the magic frictionless spandex, I could give that a push and it would keep going back and forth and back and forth and back and forth and never stop, and it would always travel in a straight line because there's no forces to make it travel in a curved path. So now Einstein says, okay, well, let's put a more massive object in the middle. So he goes, imagine this is our solar system. And this is the sun, okay? So the sun has created this huge gravitational well that distorts space and time. So now when I roll this past, now it doesn't travel in a straight line. It travels in a curved path. So Einstein says gravity, what you perceive as gravity, is just a reflection of the fact that space and time is curved. So if space and time isn't curved, and I put something there, it's not going to move. It's just going to stay right there. But if there is gravity, and I put it there, then it falls towards the bottom of that gravitational well. So when I drop this, okay, Einstein says gravity, what we observe, we can calculate it, is because the Earth is creating this huge warp of space and time. So when I let go of it, it's going to fall towards the bottom of that gravitational well. And if the Earth wasn't here, if there was no warping of space and time, I would let go of this and it would just stay right there because there's no curvature of space and time. Now, so obviously the deeper that is, the bigger the force acting on it, the bigger the acceleration is. Now, you can also do Newton's third law. Every force there is an equal and opposite force. Forces that occur in pairs. So everybody focuses on the smaller marble, but here's what you can do Newton's third law. When this thing goes by, if you notice very carefully, that bigger mass actually moves just a little bit, okay? There's a slight distortion in the path of that larger object. Now, this is where Newton's third law comes into play. Oh, for every action there is a reaction. So the forces that they're both experiencing are the same. But because this has a much larger mass, it doesn't accelerate as much. It isn't as affected by the warping of space and time like this is, because that's a deeper gravitational well. So when you do that, okay, there is some movement of that larger object, but it's just really small because it has such a large mass. Okay. So now let's say we want to go to the moon. So here's the Earth and here's the moon. Okay? So Earth, much bigger mass, much deeper gravitational well. Moon, not so massive, smaller gravitational well. Now, we do this like it's static, like it's not moving. In reality, it would be the sun. The Earth is going around the sun, and the moon is orbiting around the Earth. So I look at this like it's stationary. In reality, it's not. So like when you actually want to launch something to the moon, it's like throwing a pass to someone who's running. You don't throw the pass to where they are right now. You throw the pass to where they're going to be. So that's the analogy of trying to get something into orbit. So on a scale, this is the famous way they talked about the difficulty of putting something in orbit around the moon or landing on the moon. Was that imagine that you're on one end of a football field and you have an apple on the other end of the football field, and the apple is moving across like this. And you have a rifle and you want to shoot the apple. But you just don't want to hit the apple. You just want to nick the skin on the apple. So you're 100 yards away. You're trying to hit a moving apple, and you just want to nick the skin of the apple. On a relative scale, that's the challenge of getting something to orbit around the moon. So here's the story. So we launch, they orbit around the Earth a couple times, make sure everything is cool. And then they fire the engines to escape the Earth's gravitational well. And then we coast towards the moon. And then the moon catches us in its orbit. And we go around like this. We get done. We fire the engines. We come back like this. Now, so one of the things that we need to talk about is, and these are the calculations you can do. Something known as the Lagrange point. Okay, it's named after a French mathematician who came up with it. So the Lagrange point, and there's actually like 6 of them. We're only going to deal with 2 of them. So the Lagrange point, we'll start with the one that's easiest to visualize. So the Lagrange point between the Earth and the moon is the point where if you could take a spaceship and you could just place it right there. Okay, it's like imagine you have the capacity to take a spaceship, reach out, and you could just put it somewhere between the Earth and the moon where it would remain stationary, where it's like an equal tug of war between the moon and the Earth. Okay, so if I could put it here, and again, if you look at spacing, the warping of space and time, you're trying to find like the crest of the wells between the moon and the Earth. So that, so it's like you have this, imagine this cross section. So here's the moon, here's the Earth. Imagine that it's like a curve, it's like a hill. And you want to find the top of the hill. So here's the question. Is the top of that gravitational hill going to be closer to the Earth or closer to the moon? Tyler.
Moon.
Why?
Because the moon's force of gravity is weaker.
Beautiful. Okay? Moon has a lot weaker gravitational field. Okay? That's why it doesn't have an atmosphere. You want to be a weatherman, go to the moon. Boring. It's either sunny and hot or cold and dark. That's it. Okay? So if I take this and I put it halfway in between, it falls back towards the Earth. If I'm too close and I let go of it, it rolls towards the moon. So there's a point, this Lagrange point, where if I put it just right, it's like it's sitting on top of this hill. There's an equal gravitational pull between the Earth and the moon. Now, once it crosses that point, then it will start to fall in the gravitational field of the moon. If I go the other way, then it's going to begin to accelerate back towards the Earth. So NASA needed to know exactly where that Lagrange point was. So what they would do is they would fire the engines, they would go around, and then they would get going fast enough. Now, one of the things we'll talk about, this is on the lecture notes, is something known as escape velocity. So escape velocity is how fast an object has to go to escape a gravitational field. So if I take this and I roll it up the hill, right, and if I just roll it a little bit, give it a little bit of velocity, it comes back down. And the faster I throw it, the farther up it goes before it comes back down. Now, if I could throw it fast enough, whoop, then it would completely escape the gravitational field of the Earth, the moon, depending on, like if we want to leave our solar system, we have to get out of the gravitational well of the sun. If we just want to escape the Earth, we just have to have fast enough to escape the gravitational well of the Earth, because it depends on what you're trying to do. So if you're just trying to escape the gravitational pull of the moon, that's not very fast because the moon doesn't have a very deep gravitational well. So if you look at the sequence, so we fired the engines, okay, we go in orbit, we orbit a couple times, we fire the engines, we have to go fast enough to escape the gravitational field of the Earth, because we don't want to do this. We don't want to fire the engines and go, woo, and then we slow down, we stop, it's like, did you make it to the moon? No, we weren't quite going fast enough, okay? Got sucked back into it. Well, that's embarrassing. So you want to be going fast enough, but then here's the problem. Once you start on the other side of the Lagrange point, then you begin to speed up, okay? So then what you have to do, you want to get caught in the gravitational field of the moon, so you actually have to fire your engines and you have to slow the rocket down. Because otherwise you just kind of skip right past it. It's like, we made it to the moon, but we were going too fast and we just kind of went right past it. Well, that's embarrassing. So, but you don't want to slow down too much, because if you slow down too much, then you crash into the surface of the moon. That's awkward. Did you make it to the moon? Yeah, but we crashed to the surface of it. Oh, really? So there's this balancing act that you have to reach. You want to be going slow enough that you get caught in the gravitational pull of the moon, but you don't want to be going so slow that you crash into the surface of the moon. So that's the balancing act. You don't want to go too fast. It's like the Goldilocks zone. Too fast, bad things happen. Too slow, bad things happen. So they orbit around. So then on the Apollo missions, then they sent a command module, landed on the moon. They did their thing, played golf, measured a pendulum, all that good stuff. They come back out. They rendezvous again. They fired the engines. They escape from the moon. They cross that Lagrange point, and then they begin to speed up. Now, then you get into something called a binary star. The binary stars are cool, but the gravity gets really complicated. So imagine that I have a binary star. I have two very deep gravitational wells. So now if I look at like a moon that's trying to orbit around them, so now you have two gravitational wells, and so now all those calculations become much more complicated, because as it's moving, you're always changing the gravitational field. Because now instead of just using big G M1 M2 over D squared and finding that force, now you have to do that for both of them. So as it moves closer to one, that force gets stronger, but then this gets weaker. Okay, well then you circle around, all right, then it gets pulled into this gravitational field. Then we're going to orbit around here, but it's still within the gravitational field of this one. So that's one of the things I also want you to keep in mind. Even when we're launching like towards the moon, even after it crosses that Lagrange point, it's still in the gravitational field of the Earth. It isn't like, we crossed that point and the Earth isn't a factor. Earth's still pulling on the object. It's just less than what the moon is pulling on. So if you look at like net forces, so when you're at that Lagrange point, the net force is just going to be 0, because it has an equal pull in both directions. Once you cross that, it's still being pulled by the moon, and by the Earth, whatever that situation is, but now it's just like a tug of war. Which one is going to win? Got the idea? Good, great. Okay, back we go. Let's talk about this problem number 10 on your assignment. So here's the basic idea. Here's the Earth. Here's the moon. And you have two Lagrange points. This is what's known as L1. And then you have another one, L2, which is on the other side of the moon. So basically, here's the idea, is that if you could take a spaceship and place it right there, that would be like at the top of that gravitational well. And what would happen is that it would stay in orbit. So what that would mean is that as the moon is going around the Earth, this thing would stay locked in place between the moon and the Earth. So you wouldn't have to fire, you wouldn't have to exert any fuel, because it would stay locked in there, and then it would just move with it. L2 is the other one that's out here. So if you're an astronomy geek, okay, we launched what's called the James Webb Telescope. Okay, so the James Webb Telescope is amazing. It's providing all of these wonderful pictures that are coming back. And the James Webb Telescope is actually parked in a Lagrange point between the Earth, relative to the Earth and the Sun. So on the James Webb Telescope, it's parked out there. You have two advantages. It's in the shadow of the Earth because it looks at infrared, so it has to be really, really cold. That's why we parked it in the shadow of the Earth. Also, it's a stable orbit because it's out there in that second Lagrange point. Okay, so here are the numbers that I gave you. So here's the distance from the Earth to the Moon, and that's 3.844 times 10 to the 8th meters. Okay, so that's the entire distance from the Earth to the Moon. There we go. Now, you're also told that the mass of the Moon, if you look up there in problem number 8, the mass of the Moon is 7.35 times 10 to the 22nd kilograms. Okay? So that's the mass of the Moon. So here's the easiest way to start this problem. Is think about this conceptually. So here's the Lunar Command Module, right? And this is like a tug of war. I want to find the point where the force between the Earth and the Lunar Command Module is equal to the force between the Moon and the Lunar Command Module. Okay? So it's a tug of war. I want to find that one exact spot where the force pulling it towards the Moon is exactly equal to the force pulling it towards the Earth. Okay? It's tug of war. Boom, here we go. Now, because I'm going to be talking about forces, if I wanted to calculate that force between the Earth and the Lunar Command Module, I'm going to need three things. So this is going to be the force between the Earth and the Lunar Command Module. So I would need big G, I would need the mass of the Earth, the mass of the Lunar Command Module. Now, I don't know this distance from the Earth to the Lunar Command Module. I don't know what that distance is. So I'm just going to let that be x squared. Okay? Because it's inversely proportional to distance squared. Okay, there we go. Now, that has to equal the force between the Moon and the Lunar Command Module. Okay, so that's going to be big G, mass of the Moon, mass of the Lunar Command Module. Now, here's the story. This 3.844 times 10 to the 8th meters is the distance from the Earth all the way to the Moon. Now, what we did, and this is what I want you to think through, what we did is we said this distance here is x. Okay? So what's left over? How much is left over? Let me ask you this. I owe Emma Lynn $20. I borrowed $20 from her. Okay? Said, hey, can you spot me $20? She goes, sure. So she loaned me $20. I paid her back $15. How much do I still owe her? $5. How'd you get that? The total amount from what I already paid her, right? So that's what we're going to do here. Is this is the total amount that I borrowed. I've paid her back X. So what's left over then is going to be the total distance, which is 3.844, right? Yep. Times 10 to the 8th meters minus X, but that quantity gets squared. Okay? Whew, this looks tough. Whew, that's a lot of numbers. Now, but these are equal. That's the beauty of it. There's an equality sign here. So what can I get rid of? There's a lot. I can actually reduce this down and make it a lot simpler. Bailey, what's one thing that I can cancel out? What are some things that are common to both of those values? I can get rid of the mass of the Lunar Command Module. That would be like the mass of Jaden. Okay? I'm never going to give you the mass of the Lunar Command Module. You know why? Don't need it. Okay? It's important, don't get me wrong, but we just don't need it for this calculation. So this is why I'm not going to give you the mass of the lunar command module. You don't need it. What else can I get rid of?
G.
Get rid of big G. Okay? There we go. Now, at this point, I hate fractions, so I'm going to cross multiply. So I'm going to take the mass of the Earth times 3.844 times 10 to the 8th minus x squared equals the mass of the moon times x squared. Okay? Now, I want to simplify this at this point. So I want to divide both sides by the mass of the moon. Okay? So that's just going to leave me with x squared. So somebody take the mass of the Earth, 5.979 times 10 to the 24th, and then divide that by the mass of the moon, which is 7.35 times 10 to the 22nd kilograms. So take the mass of the Earth divided by 7.35 times 10 to the 22nd. With like a total of 4 digits. It's 80 or 90, something like that. 7.35 times 10 to the 22nd.
What did you say it should be around?
80 or 90, something like
I
that.
got 81.34.
81.34. Okay, so what that tells us is that the mass of the Earth is 81.34 times greater than the mass of the moon is. Okay? So our Earth compared to the Earth, to our moon, is much, much more massive. So now, here's what I've got. I got 3.844 10 to the 8th minus x squared equals x squared. Now, at this point, okay, at this point, there's 2 ways that you can solve this problem. I'm going to show you both. How you solve this is up to you. Okay? So here's option number 1. Now, forget that this exists for just a second. I'll get back to it. Let's say I gave you the quantity 3 minus x, and this is old school algebra 1. Old school algebra 1. I gave you 3 minus x, and I asked you to expand that. What would you get?
3 minus x, 3 minus x.
So that's 3 minus x times 3 minus x. So what would you get? Oh, I'm going to go to all of your Algebra 1 teachers and make them change your grades.
9 minus 3x minus 3x
9 minus 3x minus 3x
plus x squared.
plus x squared, otherwise known as 9 minus 6x plus x squared, right? If any of you look at this and go, what is this sorcery that you're doing? So help me God, I'm going to go to the math department and yell at them, okay? You should be able to do this without hesitation. Boom, that's it. If any of you look at this, I've never seen that before in my life. You have been done a disservice. Now, so here's option number 1. You're going to do the same thing with this. It's just lower, lower, lower big numbers, okay? So you get like this times itself, this times 2 plus x squared equals x squared. Then you would distribute the 81.34 over that number. Okay, so you'd expand it. Then you'd multiply everything by 81.34. Then you eventually want to use remember this, negative b plus or minus b squared all over 2a, the quadratic formula. Okay, right, the little song they teach you, right? Everybody remember that, okay? And all over 2a, okay? And you could do that. And you'd have to move x squared over here because that only works with one side of the equation equals 0. And it would be the most complicated quadratic formula you would ever do in your entire life. Okay? You can do that. So if you want that challenge, expand this binomial, multiply everything by 81.34, move x squared over to one side to get that equal to 0, and then plug that into the quadratic formula. Okay? And you're going to get 2 possible roots. You're going to get L1 and you're going to get L2. That's an option. So if you want the challenge, that's how you could roll with it. Here's option number 2. And again, this is just an option. I don't care which one that you pick, but you have to pick one. So here's option number 2. We're just going to take the square root of both sides. Okay? Take the square root of everything, right? So what's the square root of x squared? X, okay. Now, we're going to take the square root of 81.34. So somebody take the square root of 81.34. Nine something. What'd you get?
9.02.
9.02 times 3.844 minus x. Okay. So here's option number 2. You have 2 possible roots for the square root of 81.34. You have plus 9.02, you have negative 9.02. So here's how you're going to get your 2 possible roots. Take the positive 9.02, multiply it by distribute it over this quantity. So take 9.02 times this, and then you get 9.02 times the negative x, which is going to get you negative 9.02x. And that equals x. Then get all your x's on one side, get the numbers on the other, solve for x. Okay? That's how you're going to get one possible root. If you get the second possible root, then you take negative 9.02 and distribute that. Get your x, you got an x over there. Then get your x's on one side, get the numbers on the other, solve for x that way. Okay? I don't care which one that you do. Personally, this is a lot less complicated mathematically. Okay? But it's kind of a cheat from the quadratic. So if you're a pure mathematical and it's like, oh, Mr. Burkamp, I really need to use the quadratic formula. Okay, cool, do it. Okay? It's cool. It's the biggest quadratic formula you ever do in your entire life. Or you can take positive 9.02 and distribute it and get x's on one side, and then take negative 9.02 and distribute it and get it on the other side. I don't care which one you do. But when you get done, here's what you should see. Okay? When you get done, here's your visual. Here's the Earth. Here's the Moon. One Lagrange point, L1, is going to be between the Earth and the Moon. The second Lagrange point is out here on the other side of the Moon. Okay? So those are your 2 possible values. L1, L2. One is going to be smaller than the radius of the Moon's orbit. One's going to be bigger than the orbital radius of the Moon. Okay, now, let me give you some hints on some of these problems before I turn you loose. So, when you get to question number 2, you have 2 identical spheres separated by 1.2 meters, experience mutual gravitational force of 1 times 10 to the negative 4th, compute the mass of each sphere. So in number 2, you want to start with F equals big G, M1, M2 over distance squared. Okay, start with that. Now, you have 2 masses. You have mass 1 and you have mass 2. So if you let mass 1 equal x, what is mass 2 going to equal? Why? Yeah, because they're identical. Okay? So now, this is a simple question, but yet it's missed more than I ever want to admit. When you multiply x by x, what do you get? X squared. You don't get 2x. Okay? So don't write that as 2x. Put that as x squared, please. I don't want to have to yell at your math teachers. When you get to question number 3, at what center to center distance from the Earth would a 1 kilogram mass weigh 3 newtons? Okay? So here's the story. If I have 1 kilogram mass at the surface of the Earth, what does 1 kilogram mass weigh? 9.8 newtons, because you would take 1 kilogram times 9.8 meters per second squared. So here's the Earth. I want to know how far I have to go from the Earth so that basically G becomes 3 meters per second squared. Okay? That's the problem. So you're going to use a little g equals big G, you know, the mass of the Earth, solve for R. When you get to question number 8, You're going to calculate how fast the Lunar Command Module is moving as it orbits around the moon. So let's talk about number 8 so you kind of get a visual. Here's the moon, here's the Lunar Command Module, and it is 72.0 kilometers above the surface. You need to find on number 8 the velocity equal big G m over r. Now, where does that r have to be measured from?
The center.
From the center of the moon out to that point, and that distance has to be in meters. So you need to take 72 kilometers, add that to the radius of the moon, change that into meters, boom, there you go. What should be your order of magnitude for that velocity on number 8? 10 to the third. Okay? Then, on number 9, you're going to calculate the orbital period. What should the order of magnitude in seconds be? 10 to the third. So both your answers to number 8 in meters per second is 10 to the third, and on number 9, those seconds are 10 to the third. When you get to question number 13, okay? So if you look at how global positioning satellites work. So here's the Earth, and here's your phone. Okay? So you want to know, hey, I need to get to Dairy Queen. Punch that in. Okay, well, your phone has to keep track of where you are and where the Dairy Queen is. So around the Earth, we have this parking lot of GPS satellites. Those are like fixed beacons, okay? And you need at least 3 of these you need to bounce a signal off three of these satellites. It's called a triangulation of data. Okay, you can't just use one satellite. This is why you have to have a whole bunch of them. So your phone is always bouncing information off of these global positioning satellites. And these only work if they stay above the same position on the Earth all the time. Okay? So they need an orbital period of 24 hours. That way, as the Earth spins, they move with it, and therefore you have a series of fixed points to navigate from when you plug that into your phone. So, but notice on this one, I asked for how high above the surface of the Earth. So you're going to find a radius which is from the center of the Earth out to those satellites. Okay? Then how are you going to get the distance above the Earth? What are you going to do? Subtract out the radius of the Earth. Okay? When you get to question number 16, 16 is old school. Okay? 16 is old school. Okay? Like that equation, old school kind of thing. Okay? So 16 is old school. When you get to 18, 19, and 20, you're talking about escape velocity. The equation for escape velocity is not on your equation sheet, but it's in the lecture notes. Okay, the last page of the lecture notes is all about escape velocity. The definition, how you calculate it. Basically, the only difference is that there's a 2 involved. Okay, that's the only difference. Later on, you'll see where this comes from because energy has to be conserved, and that's where that 2 comes from. Okay. But escape velocity is not the same as orbital velocity. Okay? Let me give you some hints. On number 12, when you're finding the mass of Saturn, that should be something times 10 to the 26th. Your answer on number 13, after you subtract out that radius of the Earth, you should get something times 10 to the 7th. On 14, that answer should be something times 10 to the 5th. Let me see. Your answer to 6C, this has to do with an electron orbiting around a proton. Your answer to 6C should be something times 10 to the 12th kilograms. Both of your answers to number 10 on those Lagrange points, both of those answers are 10 to the 8th. Okay? Both of those are 10 to the 8th. So here's what we've got. So tomorrow, I'll answer any questions over this. Okay, this is actually going to be due on Thursday. So, but you want to get this done, because this is the large portion of this test. So we'll go over this, we'll review tomorrow, I'll give you the review. Test is going to be on Thursday. Okay, and that way you don't have anything to do over the 3-day break. And you can enjoy Easter. Okay, all right. Let's call it a day.